Welcome to Lecture 4.9. In this final content video of this chapter, I'll be covering what I like to call the number line of activation, which will help us understand how we can handle more than one directing group at a time. Afterwards, I'll be providing a few different problems we can work together on, and then some practice problems to try yourself. Typically, midterm cutoffs are around here in curriculum that I'm familiar with, and so a lot of practice will be given as these reactions are, at this point, really the main reactions you've learned about. So let's talk about this number line of activation. The basic idea is that we'll set a dot somewhere near the middle to say that this is the neutral point. As you move towards the right, we get more activating, and as you move towards the left, we're more deactivating. Based on the previous understanding of our groups, we could then say that the alkyl group, right, is a weak activator. It's, activating, but not as far as the strong activators. Remember that the strong activators, I'll list a couple here, right? They generally have a lone pair attached. So an atom with a lone pair directly attached. Excellent. Moving towards the deactivating side, we have our weak deactivators, which are our halogens, right? This includes bromine, chlorine, iodine, stuff like that. Even further, we then have our strong deactivating groups. This includes any pi bonds, so carbonyl-based groups, even double bonds to carbon can appear here. And don't forget about those exceptions that are still very strongly deactivating, like the CF3 group and the NH3 plus group. Right? These ones don't have any lone pairs nearby, and they just pull electron density, making them deactivating. Now, the idea, remember this key exception, it would have been very nice if the activators were orthopara and the deactivators were meta. Recall that this is an exception, the halogen, and that all three of these groups here are ortho-para directing groups. That is, if you see them on your reactant, any subsequent reaction is going to be putting the group in either the ortho or para position, whichever is sterically better. Only the strong deactivators are meta-directing. Right? If you see these on your molecule, that means that the next group is going to prefer the meta position. So with that in mind, that's awesome, right? We have this nice overview. I highly recommend that you have these not memorized, but understood, that you know how this idea works. And there's a phrase you're going to hear, which is the best activator in a moment. So what does it mean to be the best activator or the strongest activator? The reason I like this number line is it gives us some level of directionality. Really what the best activator means is the thing that is furthest right on the number line. Furthest right. So let's imagine just comparing a few groups here just to get this idea across. If I have a strong activator and a weak activator, it's very sensible that the best activator is the strong one, right? But notice that it's further right on the number line. That's not one that students typically have problems with. Here's one that they do. Take a weak activator and a strong deactivator. Now, the strong deactivator is stronger. So when I ask you what the best group is, or the strongest group, many students will say, oh, well, it's the strong deactivator. But actually, that's the worst group. It's the lowest priority, right? The strongest activator is simply the one furthest to the number line. Considering that, let's take a look at how we can handle more than one directing group at a time. The idea here is to only care about the strongest activator, the one that's furthest right. So with this small little rendition of the number line here, let's rank the substituents from strongest activator to weakest activator in these two cases. And then think about where, if we were to do another reaction, where it would go, where the next group would go. So for the molecule on the left, we have 4 different substituents. We have a bromine, a hydroxyl group, a propyl group or an isopropyl group, and an ester. So let's try to rank them from strongest activator to weakest. Feel free to pause the video and try to do that yourself. Hopefully you got an answer. Let's go through it. So the strongest activator is definitely going to be the hydroxyl group, right? It is the atom that has a lone pair directly connected to the ring. Remember that bromine does as well, but it's the exception. It is a weak deactivator, right? The OH kind of fits this rule of having a lone pair directly connected. Okay, that's great. Next would be the alkyl group. Right? The alkyl group is a weak activator, and there are no other strong activators on the ring. Then, between the bromine and the ester, notice that, again, esters, we can't memorize them as always activating or deactivating, but here we can see that it's connected by the carbonyl. That makes it a strong deactivator and our lowest priority. And bromine is third. If we were going to listen to anyone here, right, who would we listen to for the next reaction? The strongest activator is the hydroxyl group. It wants its next group to go ortho or para. The para position is already taken. This ortho position is already taken, meaning that this remaining open ortho position is where we would expect the next group to go if I was to do a subsequent EAS reaction. Looking at the second chemical, we see a benzene ring, and to complicate it a bit, we have another ring system as part of it. Right? Don't be too worried about that. We're only looking at what's directly connected to the benzene. So on the top of this ring, once again, we see that strong deactivator, right? A carbonyl that can withdraw electrons from the ring, and as such, we'll rank this as the lowest priority. We then have, on this side, an alkyl group, right? Now, that's just a carbon. Of course, it's eventually connected to a carbonyl, but from the perspective of the benzene, that is a weak activator, just in our group. And looking at the rest of the ring, I don't see any strong activators. Right? We have this one as probably the strongest activator on the ring, then the chlorine. Now, between the ester and the carbonyl, this question isn't too straightforward, and honestly, I think this one's a little bit unfair. Typically, you would want to avoid having two carbonyls at once, but the general rule of thumb is that esters are kind of busy with their own resonance here, right? That oxygen already is getting electrons there. Meanwhile, this carbonyl gets to really enjoy the resonance from the benzene. So for that reason, I would say that this ester group is slightly less deactivating, but honestly, I don't think you would be expected to know that. We're going to cover these kind of ideas much further in the course, around section 10, where we really start to deal with these carbonyls in greater detail. But for now, it's still important to recognize that regardless of which group is higher priority, it really doesn't matter, because the next question will be, well, where does the next group go? And to do that, we would only listen to position 1. Now, in this position, right, ortho-para is favored. Those are all taken. So the next one would actually have to go meta. But again, recognizing that it's really the strongest activator that we need to listen to. Excellent. Now that we've covered this, feel free to take a look at the practice questions attached, or move to my next videos where I'll work along with some roadmap and synthesis problems on this topic.